A2 Maths, Product Rule and Quotient Rule. Okay, so what I'd like you to do is have a go at differentiating this function just here. Only using your skills from year one, just have a go at differentiating that function. Okay, so pause it there and then have a go. Okay, so the first thing you should have done, hopefully, is expanded the quadratic. And then once you've expanded the quadratic, multiply it by the function at the front, the power 4 function, and then ended up with this polynomial. Once you've got this nice neat polynomial, then you can differentiate it like it's asking for there to get 12x to the power 5. 5 times 12 is 60x to the 4, and 4 times 18, 72x cubed. Okay, so those skills, no problem at all. And the reason why that was fairly straightforward is because this function just here was only squared. This function here was just a simple x to the power 4. It wasn't too bad. All right. If this was something like to the power 7 here, and maybe this was something like instead of x cubed, x to the 4, it was something like sine x or cos x or e to the 12x. Because these two functions are quite easy, we could expand it and differentiate it. Now you could probably always sort of expand some of these things and then you can differentiate if it's polynomials, but there's got to be an alternative. You've got to have a quicker way of doing it. Now the quicker way of doing it is first of all noticing why we can't just use the chain rule. We can't just use the chain rule because we haven't got a function of a function. What we have is we have this function just here, which I know you could argue is a little bit like the chain rule because it is. It's a function there and a function there. But this part just here, if I separate it out, let me just put my pen on. I'll show you what I mean. So we've got this function just here. It's definitely one function. And then you've got this function just here, which is definitely another function. So unlike the chain rule, which has a function within another function, this is definitely not the chain rule. Right? You've got to notice there is two completely separate functions. But what's happening to those two functions? They're getting multiplied. Now, multiplying is what's called the product. So notice this is a product of two functions, the 2x to the power 4, as it's showing there, and then the x plus 3 squared. Okay, so it's those two functions that are getting multiplied together. Right, if you're multiplying two functions together, then you can use what we call the product rule. So if we're differentiating, we can use the product rule. Right, just grab your notebooks out. Title is product rule. So what we got is a situation where we have two separate functions multiplied together, and we're looking for you to differentiate those. So can you differentiate this function here, which is a combination or product of two separate functions? And the way we do the product rule is we leave the first function completely alone. So whatever function that is, okay, in the previous example, it was a 2x cubed function, sorry, 2x to the power 4 function, we would leave that alone. We wouldn't change it. It would stay the same. But then we multiply that by the second function differentiated. So we differentiate that second function. Okay, so we leave that one alone and we differentiate that one. Right. It's not quite as simple as just that though. What we need to do next is we need to do the other way round. We add the next part, we differentiate the first one, and we leave the second one alone. So you leave and differentiate, then differentiate and leave to end up with this rule just here, which is the product rule. Okay, pause if you need to. Right, so let's go back to that first answer. Just check it. Yes, it's probably simpler not to use a product rule. We've already proved that. But let's just check we get the same answer. So using the product rule, the first thing we need to do is leave that first function alone. So the 2x to the power 4, I leave that first function completely alone. I don't touch it. Okay. Then what I need to do is differentiate this function. This is where your chain rule skills come into play. Inside function, outside function. Differentiation of x plus 3, just 1. Bring the 2 to the front, so we're going to get 2 lots of x plus 3. Alright, so check that with your chain rule. Plus, then we do the opposite way around. We differentiate this function just here. So now it's the first function that gets its turn to be differentiated, and that goes to 8x cubed. then you leave the second function completely alone. All right, and that's it. There's our answer. We can neaten this up a little bit. We can certainly just get rid of those multiplying signs, and you could have wrote that straight away. So there we go. 4x to the power 4, because you've got the 2 times the 2, plus 8x cubed times by that. And that's it. You could stop there, tick, or you can have a go at either factorising it, which we'll talk about later, or in this case, we're going to expand it and just show we get the same answer. So if I expand this out and simplify it, no surprises, you get exactly the same answer as the previous one. Okay, exactly the same answer. So in this case, using the product rule didn't make it simpler, but it did demonstrate that you get the same answer for that one example. Okay, so grab your whiteboard, so you could do it on a piece of paper, it doesn't really matter. Just have a go at differentiating these functions. Okay, so pause there, have a go yourself using the product rule, and we'll talk about the factorising bit now. Okay, so hopefully you got the answer. Differentiate that first bit, leave the first bit alone, sorry, differentiate the second bit. So the sine differentiates to cos, the x cubed stays the same. Then differentiate the first function, 3x squared, leave the second function alone. So differentiate, leave alone. Okay, so well done if you got that. Can we factorize this? Is there a common factor of both that and that? Right, that's the next bit. So if you haven't done that, pause and just simplify it and factorize yourself. Okay, so you should have noticed that we could definitely take out an x. In fact, we could take out an x squared. So what do we end up with in this case? X squared being taken out, x cos x, that's where the x cubed cos x comes from, and x squared times that gets you 3 sine x. Okay, so well done if you differentiate and factorized. Okay, so have a look at that. Pause if necessary. Right, so let's see how far you got then. So I leave this one alone, I differentiate this one, and then I swap it over. So differentiate that first one. Sorry, leave that first one alone, differentiate the second one. So if you differentiate the second one, you'll notice it goes to 2. Okay, so 2 times the first one left alone is where the 8 e to the 3x comes from. And then the second function just here is one where you leave that alone and you differentiate this one. What's the differentiation of 4e to 3x? 12e to 3x. So well done if you managed to get that. And even better, if you haven't factorised it, pause it now. Even better if you manage to factorise it, pulling out the 4e to the 3x, because that's the common factor with both of those, gets you 2 plus 3 lots of 2x minus 3. Now this bit, just here, that's left in this bracket, isn't very neat. In fact, if you expand it, you can see that you can simplify it even further. Okay, so rather than just factorise there, simplify as well if possible. So in this case, I can definitely see 2 plus 6x minus 9. What does that go to? 6x minus 7. Okay, so very well done if you manage to get that. Of course, it would do it just as easy to expand the bracket. Okay, and that's where you would have got the same answer. Right, so I've got this one. This one you can't expand any brackets, so you definitely have to use the product rule. Okay, so it's always making sure that you're very clear on what your product is. Okay, so it's just making sure that you can clearly see there's the first function, there's the second function, so therefore it is definitely going to be a product rule. Okay, so always being very clear on what rule to use. Right, it's not a function within another function. So I'm going to leave this function alone and differentiate this one. So leave that function alone. There it is, cos 3x. Differentiate this function. Well, sine 4x goes to 4 cos 4x. All I've done is taken the 4 to the very front. What about the other function? Now I get to differentiate this one, which is minus, because cos, remember, starts at 1 and goes down, so it's minus 3 sine 3x. Sine 4x is left alone. Can I factorise that at all? Can you take anything out of that? Well, to me, there is nothing common with both of them. Don't do something silly like taking out cos 3x, because you can see a sine 3x or anything like that. You cannot take anything out. So it's as good as it's going to get. Okay, have a go at this one. Again, pause if necessary. Okay, so this is starting to get a bit tougher because you're having to use the chain rule within your product rule. Okay, so when you look at the two separate functions, we can see that we've got that function just there, and we've got this function just here. And so it's just separating out the two functions. So what do we get then? So I will get, leave that bit alone, 4x to the minus 1 to the power 4, and differentiate this part. That's where you're going to use your chain rule. So the inside function goes to 3e to the 3x minus 5. Okay. Then you could do the other way around. Leave that bit alone. Differentiate this part. Be very careful with your chain rule. Differentiate the inside function, gets you 4. Bring the 4 to the front, gets you 16. Decrease the power by 1. Keep that function on the inside. Okay, so there's your bit of chain rule there. This is why it's important to make sure you practice plenty of the chain rule questions in previous exercise. So you're very good with the chain rule because now you're going to start to use it within other questions. Can we simplify this at all? Well, I can clearly see an e to the 3x minus 5 appearing in both parts. I can see a 4x minus 1 to the power 4 there and a 4x minus 1 to the power 3 here. So I definitely know I can take out a 4x minus 1 to the power 3. Nothing common in the two numbers, so we have to leave those alone. But I can definitely take out a 4x minus 1 to the power 3 and an e to the 3x minus 5. So it's always, this is where it gets a bit more tricky for some people. Looking for those common factors. Looking for, in this case, doing to the power 4 and this one to the power 3. Remember, you can only take out the smaller number. So yes, all of those three can be taken out, but that one will be reduced down to 1. Why is that important? When I look what's left on this side, 3 lots of 4x minus 1 to the power 1. That's where that bit comes from. On this side, I've taken out, I'm left with the 16. That's where that bit's come from. What can I do with this part? I can neaten it up. 3 times 4x is 12x, minus 3 plus 16 gets me 12x plus 13. This factor, the simplifying part, is usually what people find a bit more tricky. Okay, that's what they find hard. The first bit, usually, once you've practiced your skills, isn't too bad. Okay, right. So have a go at this one. Sine squared x. Sine squared x. Okay, so pause on that one. Right, see how far you got. See if you can do the chain rule. So if you've done the chain rule already, great. You can just watch it. If you went for the product rule, fine. Have a go at the product rule. So with the chain rule, what happens then? So if I think about the chain rule, I need to think of it as sine x squared. So I think of it as sine x squared. There is a function on the inside and there is an outside function. So what do I get? I get sine x differentiated, and that goes to cos x, and then I differentiate the outside function, the 2, and I get 2 lots of sine x. So sine x differentiates to cos x, and something squared gets to 2 lots of sine x to the power 1. So well done if you managed to get that. Now if you decided to stick with the product rule, there's nothing wrong with going with the product rule, but then you have to consider it, instead of writing it as sine x all squared, writing it as a product, sine x times sine x. And if you did that, you would leave the first function alone, you would differentiate the second function, and then you'd do the other way around. Differentiate the first function, leave the second function alone. Sine x cos x plus cos x sine x. Well, if I just swap those two around, which I'm allowed to do, then I'll get sine x cos x plus sine x cos x, which, lo and behold, 2 lots of cos x sine x. Both of those two answers exactly the same. Doesn't matter if you use chain rule or product rule. It's just nice to see confirming both of those answers are identical. Okay, so well done. You don't have to do any rule in particular. It's quite nice to be able to do both. Right, so plenty of exercises for you to have a go at. Some of those are just practicing your basic product rule. Some might involve the chain rule. Some might involve you using that to do harder questions like tangents, normals, those types of things, increasing functions, anything along those lines. So have a go at practicing all of those. Take your time with it. That could be almost like a full lesson just practicing those questions. Okay, so using your product rule, think how you use your product rule to differentiate y equals sine 5x over x. Okay, so pause it there, have a good think about it, and then replay when you're ready. Okay, so how do you write that? The question is, how would you write? Because clearly it's not a product, it's a quotient, okay, because you're doing something divided by something else, you write it as a fraction. So how can you write that as a product? Well, what you can do with over x is write it as x to the minus 1. So if I write it as x to the minus 1 sine 5x, I have now wrote it as a product with that one times by that one. So why does that help me? Well, what I can do now is I can use the product rule. I can leave that first function alone. I can differentiate the sine 5x, which is where we get 5 cos 5x. And I can also differentiate this function, minus 1 lots to the power minus 2, multiplied by this one left alone, sine 5x. Now what I'd like you to do is just neaten this up. Okay, neaten it up as best you can, and maybe try putting it back into a quotient like your original question. Okay, so pause, have a go at yourself. Okay, so how far did you get? Interestingly, to be able to divide, I need to take out at least to the minus 2. If you wrote this as over x and this part as over x squared, that would be okay. Okay, if you wrote it like this, so 5 cos 5x all over x minus sine 5x over x squared. So if you did that, there's nothing wrong with that, except now when you try adding them together, what you're going to have to do, I'm just going to get rid of that x because that x is disgusting. Let's try that again. There we go. So the only way you're going to add these two fractions together is by changing this to an x squared, because then you can put them together. But by doing that, you need an extra x in there. So 5x cos 5x, which is where that part comes from. Okay, so if you don't want to do it like this, you can do it like that with two separate fractions and then get a common denominator. Work just as well. Okay, so once you've done that, I've taken out an x to the minus 2. That's why the extra x is in there. And I've ended up with that answer. What does that mean then? Well, x to the minus 2, I can now put these two as a single fraction and end up with that. 5x cos 5x minus sine 5x all over x squared. Okay, now then, what I'd like you to do is just do a bit of spotting, a bit of pattern spotting between that part and the original. See if you notice anything. Okay, so maybe pause, just see if you can spot anything before I spoil it for you. Okay, so hopefully you might have noticed a few things. What you definitely should have noticed is it's gone from an x to an x squared. Okay, so that number there has just changed power to x squared. Also, what you might notice is on the top, we've got a couple of things happening. We've noticed we've got a sine 5x went to cos 5x. How's that happened? Some sort of differentiation. Okay, so I differentiated the numerator there. That's where the 5 comes from. Where does the extra x come from? Maybe just there. That's where that bit comes from. What about this then? Is it just a case of copying that numerator? Or is it maybe something to do with differentiating x? What's the differentiation of x? A 1. In fact, if I put a 1 in there, then you might say, isn't it just a product rule on the top? Okay, differentiate, leave alone, differentiate. Okay, so it looks like some sort of product rules going on top, and that's actually true. There is a sort of product rule going on top, but what's important to notice is we've got a minus in there as opposed to a plus. Okay, now this is where we start to look at, instead of using the product rule, because sometimes you won't be able to use the product rule. If this is something like, for example, sine x, we can't, something like sine 5x over sine x, we can't necessarily work that bit out because you can't differentiate sine to the -1. So what we're going to do, we're going to have to use something different called the quotient rule. Okay, so let's have a quick look then. How can we use the quotient rule? So the quotient rule looks like this. If I've got a function over another function, in fact, I'm writing it as a quotient, as a fraction. So I've got a function as a numerator and a function as a denominator. What do I need to do? Well, you use almost like the product rule on the top, but it's important to make sure you get it the right way around. It is always the denominator left alone first. Denominator left alone, numerator differentiated. So leave the denominator alone, differentiate the numerator. Also, why is it important to get the order right? Because there's a sign here which is different. You are taking away the other way round. So minus, you left that alone a minute ago, so now differentiate it and leave the numerator alone. So unlike product rule, which didn't matter which order you did these, it could be that one and that one, because it was adding, okay, because it's what's called commutative. This one is not commutative. It has to be in the correct order. Okay, then what? Well, because it's a quotient, it will end up being a quotient as well. You divide by whatever your denominator is squared. Doesn't matter what that is, you just square it. Okay, so if that was sine x, it would go to sine x squared. If it was e to the x, it would go to e to the x squared or e to the 2x. It would always be whatever that function is squared. Okay, even if it's something complicated like sine of e to the x, it would go to sine of e to the x squared. Okay, that formula, the good news is given to you in your formula book. Okay, so you don't need to learn it off by heart, but most of you will naturally learn it off by heart. My only bit of advice to remember which one goes first is it's always going to start off with the same function. So look at that, g of x there, g of x there. That same function starts both the numerator and denominator. But as you get given it in your formula book, you'll be fine just to be able to get a hint from there. Okay, so what I'd like to do is have a go at this exam question. Find the coordinates of the stationary point of the curve y equals x squared over e to the 3x. So not just practicing your quotient rule, but also practicing one of those more interesting questions where you have to use the gradient function. Okay, so the first thing you should always look at is what rule am I going to use? Is it a product rule? Is it a quotient rule? Is it a chain rule? What is it? Now the quotient rules are a bit of a giveaway because if it's written as a fraction, we expect to use the quotient rule. Sometimes a bit harder to spot the chain and the product. Sometimes you might have to use the product or the chain within one of these functions though, if they are asking something more technical. Okay, so let's have a look then. First thing I want to do is because they're asking for the stationary points, then I should be thinking in my head, dy over dx equals 0. My advice to you is to definitely write that down straight away because you could get the mark for just being able to write that. Okay, so the first thing you should be thinking about is stationary points involve differentiation. So I'm not sure what I'm going to do next, but I know I'm going to have to differentiate this. So that's what I'm going to do first. Differentiate that function using the quotient rule because it is a quotient, it is a fraction. Right, so the quotient rule, get from the formula book. I can do it like that. It's exactly the same. All right, so just be aware in case you see it in this format. All right, you need to learn both in function notation or in the terms of u and v. So look at it, it's exactly the same. Leave the denominator alone, differentiate the numerator. Leave the numerator alone, differentiate the denominator all over v squared. I've put this in not to confuse you, but to show you the two different ways of writing it. It's important to make sure you've seen both. So what do I do then? Well, the denominator left alone. So e to the 3x, leave it alone. Okay. Then, so I'm just doing the differentiation here. So some people prefer to do it like this. Write the u, differentiate the u, do the v, differentiate the v. So you've got it very clear, very separate. If you prefer to do it like this, great. If you don't, if you prefer to do it the other way, stick with the other way. It's fine. Either way is fine. Okay, so look what's happened. Because we've done it like this, we can literally just pick out the bits, leave the denominator alone. So e to the 3x is exactly the same. Get the differentiation of the numerator. So x squared went to 2x. So there we go. I put those two parts together. Take away, other way around. So now leave the numerator alone. That's where the x squared comes from. Differentiate the denominator. I'm putting these two parts together. So I'll get 3x squared e to the 3x. All over whatever the denominator is there, squared. Okay, so being able to differentiate, you don't need to factorize it or sort it because they're not asking you to do that. They're asking you to find a stationary point. So you don't feel you have to factorize every time, but in this case, you're going to have to factorize later on. So if you've done it, great. It's not going to do any harm. Also, you might notice that actually we could do some cancelling out on this. I've got e to 3x, e to 3x, e to 3x. So I could actually cancel out straight away an e to the 3x. That might help me. Okay, so that's what we're going to look at now. So starting with that, what can I do with it? I can actually cancel out that e to the 3x. So once I've cancelled out the e to the 3x, that's come down to this answer just here. Again, I could factorise if I want to, I could take that x out, but this is the point where I could think about what to do next. How do I work out the stationary points of this curve? What do I need to do? I need to make sure I write that statement down every single time I do one of these questions. Okay, because you never know where the marks are going to be in that exam, and you may need to have some sort of reasoning marks. If you just wrote naught equals that, you're not explaining the reason. So you'll explain to the examiner, look, I understand the word stationary points means dy over dx equals naught, the gradient equals 0. So write it down, then apply it. So naught equals that. When does this equal naught? Well, e to the 3x can't equal 0, so that's okay, that's not going to cause any issues. But when does this equal naught? When 2x minus 3x squared equals 0. So in other words, 2x minus 3x squared must equal 0. So a bit of simplifying, a bit of either factorising or just solving straight away gets you two possible answers, either x equals naught or x equals 2 over 3. Once you've got those, it is asking for the coordinates. So do not forget, do not miss out silly marks. If they're asking for the coordinates, you need the y values as well. So take your 0, substitute it in. So 0 squared is 0, e to the 3 lots of 0 is 1. So that bit's okay. So what does that get me? 0. And for this one, put 2/3 in, so 2/3 squared over e to the 3 times 2/3, that's e squared. So leave it in the exact form. Do not feel the urge to type that bit in your calculator. 4 over 9e squared is in exact form. They'll probably write that in the question. Leave your answers in exact form because e is an irrational number. There is no way of writing that exactly apart from like that. Okay. Right. So well done if you managed to get all that or followed all that. What I'd like you to do now is have a go at differentiating these functions using your quotient rules. Okay, so I'm going to pause. You need to think about how to write them, okay, as a quotient first of all, and then have a go at differentiating them. Okay, so if you didn't really understand it, then I'll show you the first one and then I'd get a chance to pause it again and have a go at the others. So let's look at tan x. So tan x can be written as sin x over cos x. Okay, so that's where the quotient comes from. So if I can write it as a quotient, now I can just follow the rules of the quotient rule, which is leave that one alone, differentiate the top one, minus differentiate the bottom, leave the top one alone. Okay, so differentiate the numerator, leave the denominator alone, and so on. All over denominator squared. So I end up with this. Leave the denominator alone, differentiate the numerator, minus, which seems a bit odd because there's a plus sign there, minus differentiate the denominator. But cos x squared is minus sin x. So minus and a minus makes a plus. So plus sin x, leave the numerator alone. There's the other sin x. All over cos x squared. Right, but what I've noticed is that you've got cos x, that's cos squared x, plus sin x, that's sin squared x. Cos squared plus sine squared. Now to me, cos squared plus sine squared is equal to 1. So 1 over cos squared, or what is 1 over cos x all squared, because I could write it, think of it like that. Okay, so it's squared outside. So I could do it like that. Is going to get me sec squared x. Okay, right, so if you followed that, but you didn't do the whole of them, pause now, have a go at these three, all right? If not, if you manage to do them all, you can have a quick look at these answers. So what do we get for cosec? Let me just get rid of that bit of writing, bit messy. There we go. There we go. That one there, you need to make sure you know how to get it. You do get given it in your formula book, but you can know how to get it. What about cosec? So cosec, as you know, is 1 over sine x. So following your quotient rule, leave the sine x alone, differentiate the numerator, which goes to 0. Then differentiate your numerator, leave the denominator, differentiate your denominator, leave your numerator alone, which gets you that. Noticing that sine x goes to cos x, that's why the minus is still there. Okay, all over denominator squared, which is where we get sine x squared from. So what do we end up with? We end up with minus cos x over sine squared x. Now just be aware that cos x over sine x is exactly the same as cot x. So really, cos over sine is cot, but you haven't got just a sine, you've got sine squared, so we're left with another sine. But 1 over sine is cosec. So that's where we get this from. Just check you're happy. Cot is cos over sine. Cosec is 1 over sine. So that gets you cos over sine squared. Okay, so cos over sine's cot, 1 over sine is cosec. Right, well done if you managed to get that. Try the same with these two. So sec on its own then. So sec is 1 over cos x. So it's very similar to the previous one. We've got cot, leave alone, differentiate it, so that bit goes. Then we've got differentiate, which goes to minus sign, which is where the positive sign comes from, leave alone, all over denominator squared. So I ended with this. Right, what's the difference here then? Well, I've got sine over cos, which is tan, but I've still got another cos as a denominator, so that's 1 over cos, which is sec. So I've got tan x, sec x. Right, that leaves the last one. So as we know, cot is the opposite to tan. So sine over cos is tan. So cot is cos over sine. Right, follow the same rules then. Leave alone, differentiate. That's why you get minus. Then differentiate sine, which goes to positive cos. Leave the top bit alone, so we get cos. Now this is a bit wrong then, because we've got sine squared, cos squared, minus on both of them. But if I take the minus sign out, then I'd end up with sine squared plus cos squared. Taking the minus sign out, just check you're happy with that. If I take the minus sign outside this bracket, it would go to plus, because that's minus sine squared minus cos squared. Okay, why does that help? Because sine squared plus cos squared equals 1. So we get minus 1 over sine squared, which is minus cosec squared x. Okay, so it's important to make sure that you know how to formulate the differentiation of each of those trig functions. And this is also why you didn't do the tan function at the same time as doing sine over cos. You knew how to differentiate sine over cos in one of the first lessons of differentiation in your second year, but you didn't do tan. That's because the only way of doing tan was understanding about the quotient rule. So now you do know how to differentiate tan. You could be asked things like chain rule questions, product rule questions, even quotient rule questions, which will involve you doing tan function straight away. That's why it's given to you in the formula book. So what I'd like you to do, please, is have a go at these exercises. Same as before, practicing those quotient skills, practicing them with maybe applying them through optimization questions, maybe stationary points, maybe equations of tangents and normals, a whole host of different things. But you have to be very efficient at both the product rule and quotient rule and the chain rule so that you can be able to get these sorts of questions. There's almost one thing you can guarantee: you will be asked product, quotient, or chain, or all three in your final exam.